We just asked about what, we're given a power series with the 2n and it ended up being cosine. What would give us sine of x? Well, let's remember that 2n is always even. So what's something that's always odd? 2n plus 1 or 2n minus 1. If you take an even number and subtract 1 or add 1, you'll always get an odd number. And we know if sine has odd symmetry, so we think we're going to be using odd numbers. So let's just try something, and then if it doesn't work, we'll just modify it. So let's try a sub 2n minus 1, because that's going to be odd. And we know from our Taylor polynomial for sine it had alternating plus minuses, so we'll try negative 1 to the n. And then it also had factorials in the bottom, like 3 factorial, 5 factorial. Those were odds. So we'll try 2n minus 1 factorial. So given this formula, should n start at 0 or 1 or something else, do you think? If n started at 0, then we'd have 2 times 0 minus 1, which would be negative 1. So we should start n at 1 here, like that. So this is a guess of a formula. Let's actually try a few terms and see how it works. So at n equals 1, we'd get a of 2 times 1 minus 1, which would be a of 1, which would be negative 1 to the 1 divided by 2 times 1 minus 1 factorial, which is negative 1 over 1 factorial. Let's try another one just to see what happens. Let's try n equals 2. A of 2 times 2 minus 1 is a of 3, which would be negative 1 to the 2 divided by 2 times 2 minus 1 factorial, which would be positive 1 over 3 factorial. Is this ending up giving us what we remember for sine? So let's write what our power series so far is. It's negative x plus 1 over 3, positive 1 over 3 factorial x cubed. I know this is the term on x cubed because it has an a sub 3 here, but we know that sine of x started out with positive x minus 1 over 3 factorial x cubed plus dot dot dot. So we've got the right general idea, but we've got a sign mismatch, SIGN, plus or minus. So let's try fixing it. What do we need to do to fix it? We could say a of 2n minus 1 equals negative 1. Well, before we did negative 1 to the n, but we got exactly the wrong sign. We got odds on n when we wanted evens and vice versa. So we got negatives instead of positives and vice versa. So instead of doing an n here, let's do an n plus 1. That way, whenever n is odd, we'll get an even number, and whenever n is even, we'll get an odd number. And then the denominator seemed like that was working. Like for a sub 3, we got a 3 factorial. So we'll just keep doing that. So 2n minus 1 factorial. And there we had n starting at 1. But we like to default to starting at 0. So how can we change this to start at n equals 0? Well, we can use the other way of formulating odd numbers, 2n plus 1. So we'll still have negative 1 to the n plus 1 because we don't want to change odd or even. Well, we'll come back and think about that. And whatever number we have here, we're going to have there. So like a sub 3 would give us a 3 factorial. So now if I plug in n equals 0, I'm going to get a sub 2 times 0 plus 1, so that's a sub 1. And if we had a 0 here plus 1, then we'd get negative 1 to the 1, which is negative, but we want, when n is 0, we want that to be that would be the a sub 1 term, that would be the x term. So we actually don't want this plus 1. So we just want it to the n there. So that's ways of thinking about things where we try it, get pretty close, then fix it up a little bit. That's a good general strategy in life and engineering and math in particular. Another moderately common power series is called the binomial series. You might remember from algebra classes like a plus b to the fourth is a to the fourth plus 4a cubed b plus 6a squared b squared, blah, blah, blah. If we do that with x, and it's common to have a 1 in there, a lot of times we're just thinking of x as like a deviation from 1. Sometimes we do that if we're talking about probabilities, like a probability of 99% is like an x of negative 0.1. It's just a little bit away from 1. So we might write 1 plus x to the fourth using the same system there. You might ask, what's the nth coefficient in 1 plus x to the k rather than x to the fourth? And that turns out to be, you can write it as k choose n, or sometimes we write it as k with a capital C there, n. And that's k factorial over n factorial times n minus k factorial. And the cool thing is, if you're careful, that even works if k is fractional. So you don't even have to have an integer there. You could have 1 plus x to the 1/2 if you wanted to take a square root, or negative 1/2 if you wanted 1 over the square root, which happens reasonably often in physics kind of problems. So this even works if k is fractional, if you're careful. I want to mention a connection here. These coefficients, there's kind of a coefficient of 1 on the a to the fourth, and then a 4, and then a 6, and then a 4, and then a 1. Also, I want to mention, you see how x is appearing here as a power series, x to the fourth, x cubed, x squared, x, and then x to the 0. So that's why this falls under the umbrella of power series. Let's take a look at the coefficients here. 1, 4, 6, 4, 1. You might have seen those in other applications. You might have also seen 1, 3, 3, 1, 1, 2, 1, 1, 1, and 1. Some places call that Pascal's triangle. Pascal was a mathematician who lived around the 1700s. Is it called that because he invented it? No, of course not. It was known almost 2,000 years before him by Pingala in India. So around 2nd century BC. And in China, it was discovered by Yang Hui. So just because it's named after someone in math usually means it was not actually discovered by that person. So that's one common power series. Another one that we'll talk more about later is called a Bessel function. And those are commonly used in vibration problems involving spheres vibrating. Like if there's an earthquake, the waves from that propagate around the world and kind of make the entire sphere shake. So sphere problem, sphere vibration, and disk vibration. And we'll even see a little bit of that in the homework. But it just has like a sub n equals negative 1 to the n, 2 to the negative 2n divided by n factorial squared. So, it's a relatively nice formula, all things considered, and it's useful in all kinds of vibration problems.